Hey everybody, it's Dr. Gray. Hope you guys are having a good start to your day. Um, we have an exam on Tuesday, and it's this time that I want to spend kind of walking through the review sheet and doing some practice problems. Basically, just give you some things to look at and evaluate for this upcoming exam. Um, so just one moment. Okay, so here is our study guide for the first exam that have coming up on Tuesday. Um, I just kind of gave some big items. And the way that I constructed this and the way that I constructed your exam was just by going through the PowerPoints and pointing out like what's an important part of this class. Now, the first thing that I've added as a part of your study guide is what are the 5 steps in drug design and development? And these steps aren't really, um, they don't really have any particular, let's see, how should I put this? These aren't like experimentation necessarily. These are steps that are um, more or less parts of like a process. So it's not like they're scientific techniques or anything like that. And the steps that are involved in drug development and design, I have to rearrange my windows here a little bit. Um, they are first discovery and development. Next is what's known as preclinical research. After that, we have clinical development. Then FDA review. And then last but not least, post-market monitoring. So these are the major parts of developing a drug and putting it on the market. Now, if we look at discovery and development, that would be basically what's the molecule that interacts with our protein of interest. Hey, I see somebody joined. If you have any questions, feel free to ask. I'm just going to be working through this study guide. So that's where we are. Next up, what are ways in which we can determine if a protein is dissolved or sorry, not dissolved, is involved in a disease? Okay, so the involvement of a protein in a disease can be done a couple of different ways. And this is on your first day's PowerPoint. I'm going to switch my share. And we're going to look at this slide right here. It's slide number 16. So slide number 16. Hey, Kaylee, do you have I see you unmuted yourself. Do you have anything you'd like to ask?
No, sorry, I didn't mean to.
Oh, okay. No worries. If anything comes up, feel free to say something. Or ask or add to the chat. I've got the chat open as well. So our recording good. Ways that we can see if a disease is, or sorry, if a protein is involved in a disease, we have 3 different major ways. One of which is genetic manipulation. What that means is that we can change how much protein is in a cell by turning it on or turning it off. So that would be making a mutant organism that basically has a gene knocked out. Alternative to making a complete mutant organism, you can look at a cell line. So you can isolate a cell and basically knock out a gene. If the protein is not made because it is knocked out, then you have a sense of what are the impacts of that? Well, is this disease caused by this protein not being present? Or is this disease caused by this protein having some crazy weird activity? After that, we've got antibodies. We can use an organism or a cell's immune system against itself. Antibodies can bind to a protein and prevent it from working in a cell. If the protein affects the disease, then blocking the activity of that protein may either cure or cause that disease in a cell. So that's part of the outcome. It could cause or prevent it from going on. We have chemical genomics. We can use different chemicals that are possibly involved in a disease and see if they bind with that protein. If the chemicals do bind to a protein and change the protein's activity in the cell, then it can be validated as a target. So seeing how basically the presence or absence or the function or lack of function of a cell in response to manipulating that protein of interest is basically what we want to do when it comes to determining if a protein is involved in a disease. Okay. Number 3, what are examples of favorable interactions and what are examples of unfavorable interactions? Okay, so here we're still on that very first day's PowerPoint, and we are right here. So organic chemistry and drug design. So in the past few days, we've talked quite a bit about these different molecules. We've talked a bit about naming different molecules. Prior to that, we looked at and talked about basically types of interactions and bonds between molecules. We talked about electronegativity, electrons being shared evenly, a polar molecule or nonpolar molecule. So interactions, that general term, is used to describe how chemicals attract and repel one another. So I always think about forces that draw things together. There's attractive forces that two things attract one another. So it's attractive forces that bring them together. Or there's repulsive forces, or there's basically unfavorable interactions that repel two groups. Now, favorable interactions, I always think about like batteries, for instance, a positive end and negative end. Those are ideal. Those are the north and the south ends of a magnet. Those two things will attract one another, and that's a favorable interaction. An unfavorable interaction, on the other hand, is when you get the north ends of two magnets and you bring them close together. Now, what happens when you bring the north ends of two magnets together? Do they attract or repel one another? They're going to repel. One of those magnets is going to do that quick spin so that its south end is closer to the north end. So our best examples of attractive or favorable forces would be a sodium ion is attracted to a polar water molecule. So that's a positive end attracted to a negative end. And whenever I say polar, I mean a molecule with a positive end and a negative end. And sometimes those charges that positive versus negative, they're not super strong forces. They're what are referred to as partial charges. Now, unfavorable interaction would be two similar forces that repel each other. So they're similar, if not identical, forces that they basically it's almost like when you have a friend who you're like, I am so similar to you, and I kind of hate you. Maybe that's because we're so similar. I don't know if you have that, but I've had that in my life where, we have so many things that are similar, like personality traits or interests or something like that. And it's like, it's too similar. You're annoying. And then you have to reflect and go like, am I annoying? Okay. So those would be favorable interactions and unfavorable interactions. So I'm looking for sodium and a sodium ion and a polar water molecule. That would be attracted or favorable interactions. Similarly, a negative charge could be attracted to a polar water molecule as well. two unfavorable interactions are just two species with the same charges, whether they're both positive or they're both negative. They're going to be repelling one another. Okay, so that is essentially what I wanted you to take away from the first lecture or the first PowerPoint. I'm going to go to the PDF, or actually I'm going to the marked up PowerPoint. So this is from our second lecture. And in our second lecture, one of the things that we talked about, what we kind of revisited, were, well, a handful of different things. One thing that we did was we talked about our subatomic particles, neutrons, protons, and electrons. Two of those have masses. Neutrons and protons each have a mass. Electrons have a mass that's basically negligible. Neutrons have no charge whatsoever. Protons are positively charged, and electrons are negatively charged. So it's important to know the charges and masses of subatomic particles. And just so anybody knows, if you have any questions, feel free to interrupt or add it to the chat and I'll answer it. But other than that, I'm just kind of working through the study guide. And if there's something else you'd like me to look at or talk about, feel free to contribute it. Okay, so which elements are important to biochemistry? I gave you the periodic table and we talked about the periodic table and shaded out most of it. The parts that we kept with respect to, the parts of the periodic table that we are interested in are 4 of our halogens, our top 4 halogens: carbon, nitrogen, phosphorus, sulfur, oxygen, and hydrogen. We have a total of 10 elements that we're interested in biochemistry and in the act of drug discovery. Now, after that, we talked about what are the differences between ionic and covalent / molecular bonding. Well, what this all boils down to, in any sort of bonding, is all related to electrons. And the question is are these electrons shared or are they not shared? In the case of an ionic bond, electrons are not shared. One atom gives up an electron and the other accepts it. In ionic bonding, electrons are given away. Now, in covalent or molecular bonding, electrons are shared. Now, this sharing, however, is a little bit complicated because when you share something, typically you're like, if we shared I guess if I shared a car with somebody else, I would say, okay, well, I own 50% of that car and you own 50% of that car. That's a great idea, but that's not the best explanation or way of understanding how different atoms share electrons. Instead, it would be what's known as polarity. So if we were to say hydrogen and carbon, those two atoms share 2 electrons. Well, it's not a 50-50 sharing. Instead, we have to look at something known as electronegativity. Electronegativity is basically how much within a bond are these electrons shared. Now, carbon is more electronegative than hydrogen, in which case that sharing would be a little bit more of carbon has 75% and hydrogen has 25%. Yeah, they're shared, but not evenly and not equally. Okay, we see that electronegativity down here. This is on the 8th slide, or on the 8th slide. Electronegativity, sharing equal or unequal between atoms or within a molecule. Then let's see, what else do we have? Ionic and okay. Next up is hybrid orbitals, and basically a question of where an electron is and where it can be shared. Now, I think the most important thing when it comes to orbital hybridization is really this right here. We have sp3d2, sp3, really what you want to do anytime I show you a molecule is look at it and say, all right, I'm being asked about what is the hybridization of this sulfur. Okay, the sulfur in the middle has a total of 6 fluorines surrounding it, making up the molecule SF6. Okay, what's the hybridization of that sulfur? Well, it's got 6 things around it. So what I'm going to do is I'm going to look at this right here. And I would say, all right, the hybridization of sulfur is sp3d2. So if I'm reading this out, what I'm going to say is I'm going to list out the number of S's, P's, and D's. I've got S, P, 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 D, D. 6 things. It's bound to 6 things. S, P, 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 or sp3, DD, or D2. sp3, D2. That's how we arrive at that sp3, D2. If something is bound to 4 things, S, P, 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 sp3. If there is a central atom that is only bound to, let's say for the sake of simplicity, it's bound to 2 things. Okay, sp. Done. If it's bound to, well, 5 things, S, P, 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 D. That's 5 orbitals that I'm combining to make 1, which is why it is sp3d. All right. So I want you to be able to identify the type of hybridization. That's important. I'll give you a compound and say, this is the central atom. What's the hybridization of that atom? And it really boils down to counting up the number of things that surround that central atom. Another example that you might come across would be, or actually, yeah, there we go. So CH4, SF6, those are both examples that you can kind of lean on and look at. We talked about electronegativity. That's our unequal sharing of electrons between atoms. And that gives way to a question of molecule and bond polarity. Now, typically, or a bond can be polar. Sorry. If a molecule has a polar bond, that molecule is not necessarily a polar molecule. What it boils down to is how many things is that something bound to, and how many polar bonds does it have? Then it gets to, well, what's the symmetry of that molecule? Here what we did was we worked on CF4, carbon to fluorine, CF4, that would be carbon tetrafluoride. That's one central carbon with 4 things around it. That would be a molecule that is sp3 hybridized. Now, is this a polar molecule? Well, you have to think about what's surrounding that central atom. And then you have to think about if that makes our molecule symmetrical or not. CF4, which is similar to what's drawn here, I'm going to go ahead and right here, CF4. That's a perfectly symmetrical molecule. So that is a non-polar molecule. But what we've got here is I replace one of those Fs with a chlorine. CF3Cl. Is that a symmetrical molecule? It is not. Therefore, that molecule is polar. So when you have an asymmetrical molecule, something that doesn't have symmetry, doesn't have an even balance of everything on 2 sides of it, then that is a polar molecule. Okay. Does anyone have any questions about basically these foundations, electronegativity, bond polarity, or anyone have any questions about basically the first 12 items on the study guide? Okay. After that, we've got the Lipinski's rules of 5. And that gives us organic chemistry and Lipinski's rule of 5. Lipinski's rule of five, these are just items that you have to remember. One, that molecule can have no more than 5 hydrogen bond donors. It can also have no more than 10 hydrogen bond acceptors. It can have a molecular mass of less than 500 Daltons and an octanol water partition coefficient, a log P, less than 5. Now, one thing that I talked about during this lecture was a molecule might have more than 5 hydrogen bond donors. It might have a molecular mass more than 500 and more than 10 hydrogen bond acceptors, breaking all of the rules of Lipinski's rule of 5, and still be an effective drug. What that point, or the point of that, is that something might break all the rules but still be an effective therapy, an effective drug. But these are the guidelines that people use to design drugs, because these typically are going to be what they're looking for. Now, what we need to know for this is what is a hydrogen bond donor and what is a hydrogen bond acceptor? Okay. Whenever you're looking for a hydrogen bond donor or acceptor, basically what you want to do is you want to look for something like this. A hydrogen bond donor looks like this. Let's go with H3COH. So this is an example of a hydrogen bond donor. Now this will be a donor because there's going to be something else. I'm going to use water as an example. H. What you're looking for when you're thinking about a hydrogen bond donor. So this will be a donor, and this is an acceptor. Look for the dashed line between a hydrogen and an oxygen. Okay, so this right here is an H bond, a hydrogen bond. Now, after you've found the hydrogen bond, then you want to look for the solid line on the opposite side of that. And that is an example of a covalent bond. The molecule that has the oxygen and the hydrogen connected through a covalent bond is the hydrogen bond donor. The molecule that just has the lone pair of electrons that give the dashed line to the hydrogen, that molecule is the hydrogen bond acceptor. So your clue should be identifying the donor or acceptor as, where is my hydrogen bond? What's it connected to? And where is my covalent bond? Now, with that in mind, the easiest thing that you can do is look for nitrogen and hydrogen and oxygen and hydrogen. That will be most helpful when it comes to identifying hydrogen bonding. Now, can I get a thumbs up, or I can proceed from here with respect to bond donors or acceptors, and a thumbs down if you want me to draw another set of examples of hydrogen bond donor and acceptor. Okay. Well, I'm going to go ahead and, you know what? Yeah, I'm going to go ahead and I'll proceed from here. And if anyone wants me to circle back, please let me know. So being able to identify a hydrogen bond donor, hydrogen bond acceptor, knowing no more than 5 hydrogen bond donors, then no more than 10 hydrogen bond acceptors. So this is really kind of like a continuation of that first one. Do we want our molecule to hydrogen bond with a bunch of stuff? We really don't. And the reason for that is, if you have a molecule that just makes like 50 hydrogen bonds. Here's one of the tricky things. Water is really great at hydrogen bonding. Hydrogen bonding gives water some amazingly powerful properties. Well, what is your saliva largely made up of? Water. You've got a lot of water in your body, water in your gut. And so if you are dealing with something that hydrogen bonds really well, then it's going to go into water. It's going to go into saliva very, very quickly. And then your body's going to process it very quickly. And maybe what you need is that molecule to go into your stomach and then get into the bloodstream, as opposed to kind of like dissolving in your esophagus or something like that. Okay, so know what a hydrogen bond donor and a hydrogen bond acceptor is. Know those rule of 5, and that will be very helpful. Now, can you determine if a molecule satisfies all of Lipinski's rule of 5? Well, if you can identify hydrogen bonds, you're halfway there. The octanol water partition coefficient, that's something you can't calculate. I'll give you that, and I'll say, does this satisfy all the, I'll give you a structure and say, calculate the molar mass or the molecular mass of this molecule, and then it has a log P of 4. So I want you to be able to do that. Now, molecular mass. This is something where, in order to calculate the molecular mass of a molecule, I'm going to give you the periodic table so that you can take the mass that's written on the periodic table, add it up, and then say, okay, well, this has a molecular mass of, 250 grams per mole. The last, like I said, is the octanol water partition. I'm going to give you that. Okay. Does anyone have any questions about Lipinski's 5 rules? So that brings us on to our study of organic chemistry. So organic chemistry, we're dealing with things that are largely based on carbon and hydrogen. There's nitrogen mixed in there too. There's sometimes sulfur or phosphorus, but for the most part, we're focused on carbon-based molecules, or hydrocarbons is what they're commonly called. Now, carbon is very unique. It likes to form long chains and rings. A carbon atom will always have 4 bonds, or will always have 4 bonds. Sometimes that's going to be a double bond and 2 single bonds. Well, a double bond counts as 2 bonds. So 2, 3, 4. So that's how we get to 4 bonds. What that means is carbon, what type of hybridization does carbon almost always have? Maybe not almost always, but when carbon's bound to 4 things, what type of hybridization does carbon have? sp3, perfect, great job. It's sp3 hybridized. That's going to be pretty common. Next up so that's organic chemistry. I want you to know the stems or the prefixes for organic molecules. And if I remember, I wanted you to know up to hexane or hex, where it's 6 carbons. Some of these I think that I also mentioned, like if you're an Ultimate Fighting fan, then you know about the octagon where they do the ultimate fighting. So that's 8 carbons. So these prefixes, I think the ones where people run into the biggest problem are prop and but. So propane and butane, I think that's where people run into the biggest problems, because that's something that, ethanol is the alcohol found in like wine and beer and stuff. And so that's almost like I've heard that before, so okay, 2 carbons, got it. But prop and but, I remember whenever I took organic chemistry, I got those 2 mixed up. And so that's where I had to focus. I was like, okay, propane 3, propane 3, propane 3. I also got mixed up because prop has 4 letters. And so I would make the mistake of being like, oh, okay, that must mean that it has 4 carbons. Not the case. Propane, butane, 3 carbons, 4 carbons. Pent and hex, well, those are going to be 5 carbons, just like shapes. Hex would be hexagon. So those are all kind of like, you've seen these before, or they're maybe a little bit more familiar. I want you to be able to take a complete structural formula like what is seen on the right-hand side, and be able to write the condensed form and write the molecular formula. Now, or be able to convert. And your exam is going to be multiple choice and short answer. Or not short answer, I'm sorry, multiple choice and multiple answer. So you're going to have to take a formula and convert that to, or take the molecular formula and confirm that it matches with the complete structural formula. Then here was just kind of application of rule of 5. Now we'll go to aliphatic compounds. This is where we were really focused on alkanes, alkenes, and alkynes. We also got into cyclic hydrocarbons, but if you remember, ANE, nothing but single bonds. ENE, at least one double bond. YNE, at least one triple bond. So when it comes to butane, butane is a molecule that has 4 carbons and nothing but single carbon-carbon bonds. With respect to alkanes, the melting point increases as the number of carbons increases. Similarly, the boiling point, physical properties increase as molecular weight, or as the weight of molecules of these things increase. Now, these long chains, like what we see with butane, for example, it's 4 carbons long. Well, those carbons can have modifications to them. They can have what are known as alkyl substitutes. And so an ethyl group can be added to it. A propyl group can be added to it. Now, that becomes challenging when you see a molecule like this. I remember when we were talking about this molecule in class, one of the things that is definitely confusing about this is, where do you start your numbering? Do you start it from the right-hand side or from the left-hand side? So let's imagine for just one moment, I'm going to use white to scribble out the numbers here. So let's imagine that's not there. Boop, 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 boop. Okay. So in this case, if we were to start our numbering from the left, that'd be 1, 2, 3, 4, and then we've got 2 directions. We could go this way or this way. We'll call this 5. We're trying to come up with a straight chain. Okay. Now, we would call this pentane, because it is a 5 carbon long chain. And then what we would do is we'd say, okay, well, off of that 5 carbon chain is a methyl group, or a methane. A 1 carbon group comes off of this. So we say methyl. Rather than methane, we drop ANE and we put YL. So methyl pentane. Now, the way that I've numbered this, we would call this 4-methyl pentane, because on our 4th carbon, that's where we have this methane. Now, we don't do that, and that indicates that our numbering scheme is wrong. Well, why is it wrong? The reason that it's wrong is because what we're looking to do is use the lowest possible numbers for our modifications. So we start numbering from the right. 1, 2, 3, 4, 5. And then what we say is 2, well, pentane, a methyl group, and carbon number 2 is a methyl group. So, or on carbon number 2 is where you find your methyl group. So that's what there is to basically your prefixes and your nomenclature. Now, as we proceed from our alkanes it can get a little bit trickier when we have alkenes, in part because our formula is different. So how many carbons does a molecule have and is an alkene? Well, if it has 50 carbons, then it's going to have exactly 100 hydrogens. If it has 140 carbons, it's going to have 280 nitrogens. Meanwhile, if it's an alkyne and it has 140 carbons, then it's going to have 278 hydrogens. So we're basically using numbers and trying to come up with the smallest possible numbers to put our prefixes. So if you look on the left-hand side here, we've got a straight chain that is 1, 2, 3, 4, 5, 6. 6 carbons with one double bond. That's a hexene. Our functional groups, or our unique parts of this molecule that make it not hexane, are found on carbons number 2 and carbon number 3. So this is 2-methyl 3-hexene. The alternative, if we started numbering from the right, what would this be? If we started numbering from the right, that would be carbon 1, 2, 3, 4. It's a 4, 5. Okay, 6. So it's hexene, but then it'd be, let's see, 5-methyl 3-hexene. Okay. Does that accomplish what we're looking for by giving us the lowest possible numbers? No, it doesn't. 2-methyl 3-hexene gives us the lowest possible numbers. So that's what we're looking to do with this kind of numbering scheme. Then alkynes, you have at least one triple bond. And you indicate where that triple bond is. So 1-butyne, well, carbon number 1, that's but, would be 4 carbons. Butyne, there's 4 carbons in one triple bond. So 1-butyne shows that our numbering is going to start from the right-hand side. Now, I'm using right-hand side versus left-hand side. I want to caution you about that because if the molecule is on the right-hand side, is this molecule stuck in space or is it moving? Yeah, it's definitely moving around. So the right-hand side is all relative. It's, 1 second it's on that triple bond is on the right-hand side, then that molecule rotates in space and your triple bond's on the left-hand side. So it's, when you're drawing these, I think that it's helpful to start from someplace, but your aim shouldn't be, well, I want to put my group on the right-hand side. No, you want to give your group the lowest possible number for that straight chain. Okay, so that's our alkanes, alkenes, and alkynes. Last but not least in this is our cyclic hydrocarbons. How many carbons are there, and what double bond does it have, triple bond, or only single bonds? Cyclohexane versus cyclohexene. The difference is one triple bond. So that's all there is to it. Could you have cyclohexyne? Yeah, sure. That is basically the same appearance as cyclohexene, but there's a triple bond there in that same place. All right, we got 2 left. Functional groups. Now, I'm going to take a pause here. Does anyone have any questions, or would anyone like me to clarify anything? Okay. Okay, so now we're moving on to functional groups. And this is kind of like, I guess, our nomenclature are alkanes, alkenes, and alkynes. And then hydrocarbons is kind of like we just had a meal with steak and potatoes. It's good. It's tasty. There's a lot there. Now we're expanding our palate. Now we're adding to our meal. Now we're having a steak that has had salt and pepper. And we're adding like bacon bits and cheese to our potato. So what are we doing? We're leveling up. We're making both of those things infinitely tastier. Okay, so in this, what we're going to talk about primarily are, well, we're going to elaborate on alkenes. We have cis and trans isomers of an alkene, where a cis isomer is you have groups that are on the same side, whereas a trans isomer has groups on opposite sides. And I always like to, if we look at butene here, we've got our double bond kind of at our equator, and then we have the CH3s both up. Trans butene is, let's imagine my arms as the double bond. It's going to look like this. This would be a trans isomer, cis isomer, trans isomer, cis isomer, cis isomer, cis isomer, trans, trans, cis, cis, and so on. So just find where your double bond is and say, okay, are they both on the same side or on the opposite sides? We talked about cyclic hydrocarbons, chair conformations, aromatic groups, aromatic molecules. So an aromatic compound is a carbon structure, but they have alternating double bonds that result in a hybrid structure. So when we talk about aromatic compounds, these first two on the left are really less of the show and merely kind of possible structures. It's the one that's on the right that is the structure that's of most interest. It's the one that's on the right that illustrates like, hey, these double bonds aren't stuck between these carbons and these carbons. Instead, they're kind of between all of the carbons in some senses. They're what's known as a word that organic chemists and biochemists and chemists in general use is they say delocalized. So that means they don't have a specific location. Then from here, we will go on to, let's see, yeah. So here's some examples of aromatic compounds. Halogenated compounds. These are also known as organic halides. And these are just, you have a molecule, for instance, 2-iodopropane. Propane has 3 carbons. So we've got 1, 2 in the middle, and 3. And on that second carbon is an iodine. So it's iodopropane. Then after that, so when it comes to halogenated hydrocarbons, it's really just a matter of what is the halogen that has been added to our molecule. And our halogen substituents are fluorine, chlorine, bromine, and iodine. And earlier, we talked about you having to know about like 10 atoms or 10 elements. That's 4 of them. Carbon, hydrogen, oxygen, sulfur, phosphorus, that's 5. Carbon. I must be missing someone, one of them. But that's basically what it is. What's the identity of that element and which carbon is it on? With the case of like 2-bromohexane. What I always like to do, and what I think is a really good thing to do, if you were to take this 2-bromohexane and do this, okay, how does that change our molecule? Well, let's see. It's still a hexane, but it's actually a hexene. So 2-bromo, and then we want to say where our double bond is, and that would be 2-bromo-3-hexene. So that says that our double bond is on carbon number 3. All right. So taking a molecule and just adding a little bit more to it, how does that change its name or anything like that? There's our chlorinated hydrocarbons, fluorocarbons. Now we're on to alcohols. Okay, so can you name an alcohol? If you look at the bottom left, you've got ethanol to ethanol hydrogen bonding. I'm going to label A and B. Which one of these, add to the chat, A or B, is the hydrogen bond? Let's go with donor. Is it A or is it B? Add it to the chat. And this is totally a test question. Which one is the donor? A, that's absolutely right. A is going to be our hydrogen bond donor. That means B is our hydrogen bond acceptor because B has the oxygen with the dashed line. A has the hydrogen with the dashed line. Great job, Alondra. So that's what you should be looking for. That's the sort of question that I will ask on the exam. Alcohols have hydroxyl groups. Because they have hydroxyl groups, they're great for hydrogen bonding. There's methanol, ethanol, 1-propanol, glycerol, T-butanol. If you look at glycerol, that's kind of got a unique name because you could also call that, let's see, 1, 2, 3 carbons. So that would be propane. And then if you add alcohol there, a 1 hydroxide group, that makes it 1-propanol. So if you had glycerol, what do you think would be another name for that? It's based on propanol. You've got 1, 2, 3 tripropanol because you got 3 alcohols, or propane triol. You've got 3 alcohols and 3 carbons. Now that would be kind of like a bonus sort of question that I'd throw on the exam, which I might throw maybe 2 or 3 or 1 or 2 bonus questions on there. All right, last but not least, this one had quite a few functional groups. And all of these functional groups are kind of similar to one another, in the sense that, or sorry, there are some strong similarities, but also some differences between these. So phenols are organic compounds with hydroxyl groups attached to an aromatic compound. So a phenol is a ring plus OH. A phenoxide ion is a ring plus an O minus. Phenols love to hydrogen bond because they are also alcohols. Ethers and epoxides. Epoxide is a term reserved for, well, a 3-membered ring. A 3-atom ring, but one thing that's important to know about that epoxide is there can be modifications to those carbons on that ring, like I drew the other day, where it was like, yeah, this is a ring, but it could be this. And this one could be like this. My drawing notwithstanding is like a big factor there, so please disregard my poor drawing. Ethers, what you're looking for is basically an organic molecule followed by an oxygen followed by an organic molecule. That's an ether. We've got diethyl ether as a good example of an ether. We've also got tetrahydrofuran. It's tempting to call that an epoxide because it's a ring, but it's not a 3-atom ring, so it's not an epoxide. After our ethers and epoxides, we've got aldehydes and ketones. With aldehydes and ketones, we are looking for a carbonyl carbon. And then what follows that carbonyl carbon? In the case of an aldehyde, it's a hydrogen or a carbon or a organic molecule. With a ketone, it's organic molecule, carbonyl, organic molecule. For your carboxylic acids, well, sometimes carboxylic acids are labeled COOH for shorthand, and that would be, here's our C, and then we bring this O down, and this is just for writing, not for like, oh, this is an actual depiction, but COOH, there we go. Now, the difference between a carboxyl and a carboxylic acid, when we talk about a carboxyl, we're just talking about these 4 atoms. When we talk about a carboxylic acid, it's those 4 atoms plus any of this organic group that's added onto that. Okay, clear. Esters are formed by replacing the hydrogen of carboxylic acid with the alkyl group of an alcohol or a phenol. So with an ester, we're taking an alcohol and slapping it to the other side of that molecule to make, or to that ester, or to that acid, and making an ester. Some examples, like I said, esters were that class of compounds that have odors or that are odorous. And so that's kind of a good test question there. What class of compounds are produce an odor? Amines also produce an odor, but they're more of a cleaning odor. Um, Less than like esters produce like a fruity odor to them, whether it's pear, pineapple, anything like that. Amines, we've got a nitrogen, and it's either bound to two hydrogens and an organic group, or an amine that is bound to two organic groups and one hydrogen, or an amine that is three organic groups bound to a central nitrogen. And then our last but not least are amides. Amides are super important in protein structures. And that's a carboxylic acid plus an amine to make an amide. Now, I think that it's worth your time whenever you see amide. What are the reactants, or what are the things that come together to make that? Similarly, we'll zoom up or we'll scroll up a little bit. What comes together to make an ester? An acid, an alcohol. You don't have a huge number of these, but I think whenever you remember the reactions that come together, what do they make? Yeah, and I've got that as items number 29 and 30. What reactants, or what must react to form an ester? What must react to form an amide? So I'm going to go ahead and switch my share and show you this. I mean, this is the study guide that I provided y'all with. That's where everything's going to be coming from. So please use that and check it out, pay attention to it. If you can answer all these questions, you're going to be in great shape. I'm really not looking to ask questions that are like super in-depth, ninth level. I've analyzed this 35 times over and done this and that. I like to ask questions that are straightforward. And my plan is to ask questions that are straightforward. I've got questions on this study guide that are, can you name an alcohol? Okay, well, I mean, that's kind of a yes or no question, but if I give you an alcohol structure, I want you to be able to name it. And so that's kind of where I'm coming from. You'll obviously have a better sense of the sorts of questions that I'll ask after this first exam. But I'm not trying to like deceive or trick anyone. That's not really my game. I don't think that's worthwhile for anyone. I'm going to go ahead and stop my share though. And I will open the floor for any questions, but if nobody has any questions, you're welcome to leave at any point. This is totally voluntary. But I hope you have a great weekend. And if you have anything, contact me by Monday. Deal? Okay. See you, Alondra. Absolutely, Miles. Have a good one. I'm gonna, it's probably gonna take, it usually takes like 15 minutes to process, and then it'll get posted to my YouTube shortly after that, and then I post it to Canvas. So I think that it's pretty safe to say by 3 p.m. Barring that I don't accidentally take a nap right now. I don't plan on that. I'm planning on just getting them posted up before 3 p.m. And I'm gonna stop.